All right, this mini lecture is going to look at much more detail of diffraction, the mathematical representation of the diffraction pattern that we get, the light and dark spaces on a screen when we observe light moving through a small slit. So that idea of the wave nature of light and that bending around that barrier, that small opening. When we have a slit, we can look at a very specific pattern on a screen that has bright spots and bright bands and less bright bands, and of course dark bands in between. And so we're going to look at the single slit diffraction pattern as we develop these ideas. So we're going to simplify it as much as possible in terms of the most simple situation, observe that phenomenon, and then in a later video we'll talk about some changes to that and more complex systems. So what do we mean by a single slit? This simply means that we have just one small space, one small slit in a barrier that we're going to send light through. And when we look at diffraction happening that has an impact, where we can actually see the bands that occur, we need to make sure of a couple of things. The first is that this width here, this space, we call that D. So this is the width of the slit. That D is on the order of the wavelength of the light that's going through it. So if I'm sending a red beam of light through that slit, it's on the order of the wavelength for red light. I think it's 530 nanometers. Okay, so very, very tiny on the order of the wavelength. The other thing that we need to keep in mind is that the screen is really, really far away. Okay, so the length, this distance, we're going to call L. L is our distance to the screen that we're observing the pattern on. L is much, much bigger than the slit width, so really far away. We can't observe these patterns, these bands, unless we're pretty far away to see them, to really see the constructive and destructive interference that's happening with those rays of light. All right, let's take a look at how this actually happens. So I want you to imagine a light source that's coming through this single slit, and the angles at which light is traveling through that slit are going to be different depending on which rays you look at. So if you have a point source of light, remember through our discussion of light that light rays are moving off in all directions, right? So they're coming onto this very, very tiny slit in multiple angles. So let's look at each one of those. We're going to look at a few different angles, not every one of them. We're going to look at through three gross angles so that you can get an idea of how the diffraction pattern on the screen is formed. So let's make a barrier here. I'm going to keep this information up for a bit. All right. So if I have parallel rays of light coming in to this slit. Now I'm making the slit much larger, okay, just for our visual ability to see what's happening. Keep in mind, again, that this is very, very tiny and on the order of the wavelength of the light that's coming through. So if we imagine the parallel waves of light coming through on the screen, they're going to come through and they're going to hit the center of that screen in a bright spot. So we're going to get brightness right at the center of that screen, right? They're going to come through and they're going to give a bright spot on the screen. All right. That one's not pretty, that's not too difficult to figure out. What happens if instead the light rays, they're the light rays that are coming at an angle. So now light rays are going through at an angle. Okay? And we know that with a point source of light, there are certainly light rays that come through at an angle. Okay, so let's imagine we're really, really, really small. We're on the order of wavelength. So a lot of them are coming through parallel. Okay, and that's going to be our model. A lot of them are coming through parallel at this angle. Here's where things become fun and important. All right, so this angle here, this is our angle theta. All right. If the rays travel through an angle theta, and the top ray, if this angle theta, I'm just going to draw a perpendicular line here, okay? Here we are perpendicular, all right? For this perpendicular line, this angle theta tells us this distance here, if that distance there, so this distance here, okay? This ray of light on the top, we're going to call it ray A, and I'm going to say this ray of light on the bottom, A, B, C, D, E. Ray A travels one wavelength longer, further than ray E travels when they hit the screen. So when they come in at an angle, ray A travels one wavelength longer than ray E. So ray A travels one wavelength longer, more distance than ray E. Okay, so hopefully you can see that if I draw that kind of perpendicular line. Well, what does that mean? Well, that means that halfway in between ray A and E, half a wavelength is traveled by the ray halfway in between. Which means this ray halfway in between and this ray E hit the screen shifted by 1/2 wavelength. They hit the screen shifted by 1/2 wavelength. So you can imagine that if I have a wave, so I'll call that's the one at the halfway point, and it shifted by 1/2 wavelength. So half of a wavelength. Half a wavelength shifted. Blue is shifted over by half of a wavelength. What happens to these waves? We get destructive interference. We get destructive interference. Which means when those two waves hit the area on the screen, we see nothing. We see a dark spot. And that happens, there are pairs throughout that whole barrier. So the pairs make up this destructive interference. When the angle causes that wavelength to be one wavelength, causes that light ray to be one wavelength, we get destructive interference. Furthermore, if the angle theta is twice the wavelength, 3 times the wavelength, 4 times the wavelength, any integer value, if it manifests 2, 3, or 4 times the wavelength of a distance separation between the top and the bottom, we get destructive interference. And this gives rise to an equation that tells us the sine of the angle theta is equal to the wavelength over the separation width. And that's just the geometry manifested by this green triangle that I wrote here. So you can look at the geometry to get that relationship. That's just trigonometry. But it gives us important information such that for every angle where the sine of the angle is an integer value of lambda over d, we get a dark spot. We get an edge that's dark. We get destructive interference. And so dark spots occur at d sine of theta times lambda. I'm just bringing d up over here, where m is equal to 1 plus or minus 2, so on and so forth. So we get them at the top and we get them at the bottom. So that is where the edge is. My first dark spot at the top will be when m is 1. My second dark spot at the top, m will be 2. My first dark spot at the bottom, m will be 1. If we're looking at this, my first dark spot second dark spot, excuse me, at the bottom, M will be 2. Okay, so that's how we get our dark spots. So, destructive interference. All right, encourage you to pause the video, kind of think through that, maybe look at this geometry. And this triangle and that triangle are the same, so this is our diff D, this becomes our lambda. Okay. I drew this sort of, this is the lambda we want to, this line should really look like this. That's that line. Sorry, I was trying to make it visible and I realized that could look wrong. So this is D, this is lambda, and then this angle and this angle are the same. Okay, let's look at another angle, or a different angle, what might happen. That's how we get our dark spots. I'm gonna just put this over here. D sine theta is equal to lambda, m times lambda. I think that's what I wrote. If I put a D over there, I'm sorry. D sine theta equals m times lambda, where m is plus or minus 1, plus or minus 2. This gives us our dark edges. Okay. Our dark edges are our dark areas. All right, let's look at a different angle. So here is our barrier. Okay, and there's our slit. Again, it's super, super small. I'm just making it big. And here's our light leads. We're going to come through at a different angle now. Okay. This is our angle theta. And we're at an angle theta such that, I'll go ahead and I'll draw this perpendicular again, such that this length, I'll draw it on there, it's a little bigger so it's easier to see. If this length is 3/2 lambda. Right, so what does that give us? If my angle is as such that the length at this top ray, A, travels 3/2 the wavelength, so 1.5 times the wavelength as our bottom most ray B. What happens? All right, well, between 3/2 and that, the distance traveled is lambda more than 1/3 the way down, right? So about 1/3 the way down, right? So if this is 3/2, I have a half, okay? So 1/3 of the way down of this slit, we get to the lambda distance. And what did we learn from the lambda distance in our previous example? Well, everything, the ray lambda, halfway between that, we get destructive interference for every ray. And so 2/3 of the space are destructively being interfered with in a destructive way, so we're experiencing destructive interference on the screen. However, 1/3 of the space gets to the screen. So we get some light on the screen. It's not as bright as the center, but a portion of that light gets to the screen. A portion of that light is destructively canceled. All right? So when lambda is 2/3, we get our bright spots. So we can turn that, 3/2, we can turn that into an equation where, again, d times the sine of the angle is equal to lambda. That's just my triangle relationship. That's just trigonometry. Oh, I missed the m. But if m is now 3/2 lambda, 5/2 plus or minus 5/2, I guess it's not lambda, the m is just what it is, 3/2, 5/2, 7/2, and so on, we get our bright spots. Again, not as bright as the center, and they get dimmer and dimmer as the angles get bigger. And we'll talk about that in just a minute. Not as bright as the center, but we in fact get those bright spots as well. All right, so that gives us a relationship for our bright spots. And I think I'll just put down here. So I'm still on the screen. All right, that gives our bright spots. Whew, so we have 3 different ones that we've looked at. What does it look like actually on the screen? What do I mean by these bright spots and these dim spots? Well, if you can imagine that the bright spots are kind of like mountains. So we're going to draw how these bright spots might look. Keeping in mind that we have light coming through this slit at all different angles. And as such, so I'll just erase this. Start over, I guess. All right. So here we have our slit, very, very tiny, not a pinhole. We have our light source here. And what do we see on that screen? So again, the screen is really, really far away. Right at the central, we see a maximum of light. And then as we go outward, we see additional light areas, and then we see these dark areas, all right? So the maxima is flanked by 2 dark edges, given angles, the angles that have the relationship where M is 1. The bright spot given angles where the relationship of M is 3/2. Right? So that's sort of how we can visualize the bright and dark patterns on the screen. Now, in addition to that, and keep in mind these 2 things are still really important, where the distance D is on the order of the wavelength, and L is really, really far from the screen. So we can look at these patterns, knowing our slit width and our distance L, we can look at these patterns and we can determine the wavelength of light, which is actually a pretty nice feature. It allows us to know what the wavelength of light might be. So how can we use L? What's the geometry? I just want to go through that real quick on how we can sort of use some of this information. Keep in mind that if I go straight down the center here, that brightest spot, that brightest individual spot, that is the spot that the light is going straight through, right? That's the spot that the light's going straight through. This width, well, maybe it was different color. This angle theta, that's to our first dark spot. On the bottom, this angle theta, which are identical angles, that's to that first dark spot on the top. So 2 theta is the angular width, we call this the angular width, of the big bright spot, which is called the central maximum. 2 theta is the angular width, 2 of each of these, right? That's how wide it is angularly of this central maximum. All right. We can get the actual width, of course, if we know the length. So if I know the length L, I can simply get the geometry, this width. Okay, so if I know the length L, and this is the width I'm interested in, and this is the slit width, the tangent of theta, so the tangent of this theta, we know is equal to the width of my central maximum times the distance. Or sorry, divided by the distance, divided by the length. So here's my angle. Here's my length. Here's my width. Here's the angle that makes. So the tangent of the angle is the width of my central maximum divided by the length. So L tangent is equal to my width. And if I multiply that by 2, I get my total. So my total width in meters, is twice this height there, that width there, right? So I can get the angular width and I can get the total width of the central maximum. Okay, so just a way to take the width of this and to think of it in two different ways. That central maximum from an angular perspective, we know the angles, we can get information about the wavelength of light, or vice versa, if we know the information about the wavelength of light, we can get these angles that are going to be that central maximum angles. We can see how wide that central maximum is going to be from a measurement perspective, from a length perspective in meters, if we just do a little bit of geometry. Similarly, if we move to the second and third bands or barriers, dark spots or light spots, we can get the width of that diffraction pattern, and we can describe the diffraction pattern in terms of its bright spots and its dark spots. Now, there's going to be a width, a distance, an angular width that the light is gone. That happens related to the sine of that angle. Remember, sine of an angle can't go past 1. So when my integer value or fraction value times the wavelength divided by the distance, the distance of the width goes greater than 1, we no longer have the phenomenon. Okay, a lot of information. I encourage you to kind of rewind all that, kind of go through it a little bit slowly. It's difficult. This is sort of those types of lectures that you kind of want to pause and see the feedback of my students and make sure we're following the angles and the geometry and all of the different pieces to keep in head. So go through it again slowly. And this is the idea of the mathematical representations for single slit diffraction. We're going to do an example problem in another video, so check that out using all of this information. All right, good job.